So now that we proved in the particle in a box model that the energy of electrons can be completely calculated just by using the wave-like nature of electrons, now we're opening the door to coming up with more sophisticated wave models, and that's where Schrodinger came in. And you may have heard of Schrodinger through the Schrodinger's cat, which is a probabilistic model of looking at electrons. And Schrodinger's cat, it's the idea that if I put a cat in a box and I put a poison in it, how can we know if the cat is alive or dead in the box? And the idea is that the cat could be alive or dead in the box, and the only way we can find out is by actually opening the box and seeing. And in the act of opening the box, the cat will then choose one of those probabilities. So it's a complicated model, and in the scope of what we do in IB physics, we're scratching the surface. We don't really know how to calculate that. It requires a little bit more calculus and something you would do in probably second or third year university. You can see it in the background over here. But what we need to know is that Schrodinger took a look at the model and was able to say, okay, if we know the momentum of an electron and atom, then we can calculate the total energy and solve a wave function. What a wave function is it's plotting the displacement. It's looking at the electron just as a simple harmonic motion oscillator. And if I know the energy of it, I can then map the oscillations trapped within boundaries, and I can provide a graph of the displacement of that wave for an electron over time. And it's a little bit more complicated than that. He's plotting it in 2 dimensions, so you can get a bit of a model of displacement amplitude over the radius of where that electron is. And then what happens if you square that wave function, what you'll get is the probability. So this Schrodinger's cat model is a probability model. Instead of looking at electron waves as something that I can predict exactly where an electron is, what Schrodinger said is instead of looking at things in absolutes, we should be looking at things in terms of probability. And the wave function allows us to see there's a probability of finding an electron in a certain space and time. And if you think about it, when you look at a standing wave, it's vibrating. What you're seeing, if you look at that quickly, is that, there's a chance that I'll probably find the greatest chance of finding an electron would be where the greatest amplitude. If I put my finger at the greatest amplitude, the chances are I'll hit an electron. If I put my finger where there's nodes, I probably will not find an electron at all. So if I think about an electron as a wave, we need to think about where that electron will be in terms of probability. And that's what will happen if you square the wave function. So below here, I have examples of graphs of wave functions that are plotted the standing wave over displacement or the radius where it would be in the atom. These little dotted lines would be like the actual radius of the atom. You can see that the wave function kind of goes beyond the radius of an atom. But if I take a look at the lowest energy electron, it would form a standing wave that kind of looks like that with no nodes. Here are boundaries that it's reflecting within. And then if I go to the next harmonic, you see there's a node here, 1 node, okay, and then we have more nodes, 2 nodes, okay, 3 nodes for the next harmonic. Okay, and these electrons should have higher energy. The more nodes I have, the higher the energy that electron is, the more momentum it has. Okay, and if I square these graphs, what I'll get is the probability. So all the negative parts of that graph will go up. So here is the square of that graph. Okay, and anything that is on the x-axis has 0 probability. The greater the amplitude, the greater the probability of finding an electron in that space. Okay, so here I would have 0 probability, here I would have the greatest probability. So for the lowest energy electron, okay, it would look like this, where the greatest probability is finding it closer to the center of the atom. Okay, the amplitude of the wave would be greatest over there. The second energy, I would have 0 probability of finding it at the center, and I would see it in 2 different areas at the same time. So there's an equal probability of finding that electron in 2 different areas at the same time, which is quite interesting. Here I got 2 equal probabilities at 2 different, a smaller probability in the center, but there's 3 different areas that electron can exist at exactly the same time. And here is 4 different areas that electron can exist at exactly the same time. Okay, so what does that look like for chem students? For chem students, you guys have talked about this more than physics students. You've talked about orbitals, like s orbitals, p orbitals, 2s orbitals, which is a larger, it's the next shell of an s orbital. And this is what the wave probability function would look like for a 1s orbital, a 2s orbital, and a 2p orbital. So if I look at that, I would see that, yep, I would have a spherical model for that probability function. Okay, and if I look at the 2s, I should have a much larger sphere, but within it, I have a node and a small sphere in the center. So what we don't see in models that we see in their chem textbook is there's an actual smaller sphere encapsulated in that larger sphere for a 2s orbital. Okay, so for a 2s orbital, there's a great probability of finding an electron further away from the nucleus because it has more energy than a 1s electron. Okay, and for a 2p electron, I have 0 chances of finding the electron near the center, and it looks like I have the greatest probability of finding that over here. And what that would look like in 3 dimensions would be a dumbbell p orbital, where I have 0 probability of finding an electron at the middle. And then here's our dumbbell, where the energy is telling us that that would be the greatest amplitude right over here of finding an electron. It would form some dumbbell-shaped orbital. Okay, so that's for the chem students to try to make sense of this, of Schrodinger's model. That's where your orbitals, your s, p, and d orbitals came from. And here's a sample problem. What can we expect on an IB exam? Well, not much. All you can expect is maybe some multiple choice questions where they'll draw graphs of either wave functions or probability functions. And remember, if it's the probability function, it's going to be a square over here, right? So that's how you can tell whether it's probability or just the wave function. Another way of telling it if it's a probability function is you should have no negative values in a probability function because it's squared. So here the graphs below represent the wave functions of 2 different electrons. I got this guy and I got this guy. And a question could look like which electron has higher momentum and energy in this graph, A or B? Which has higher momentum? Well, if I look at this, I would say, A has less nodes, B has more nodes. What I remember from up here is that the more nodes I have, the higher the energy is going to be. It's a greater harmonic, for example. So it has more momentum, more energy. It's further away from the nucleus. All right, so then I would say that B has the higher energy because it has more nodes. And for both, where are regions of lowest probability of finding electrons? To find the probability, I got to square these wave functions. So if I square them, let's just change the color of this. So if I square them, what it would look like is, well, it shouldn't look like that. It should be greater than, it should be double the amplitude. Sorry. So all these should be double the amplitude, but they should all be positive, okay? And then here I would do the same thing. I would double the amplitude, okay? But where I would find 0 probability would be at the nodes, all these nodes. You see there's 0 amplitude over there, 0 amplitude, 0 amplitude, 0 amplitude, 0 amplitude. Okay, at those places would be a 0 chance of finding those electrons, okay? And that's it.